Welcome again. Now in this lecture I will define the half range series for sine and cosine, and then we will try to solve some questions related to the half range series. So first of all, define the half range series. Half range series. Here I am defining the half range series for the interval minus pi comma pi. So first of all, let us define half range cosine series. Let fx be an even function. Even function means f of minus x is same as fx. So if f of minus x is fx, then our a naught, let fx be an even function in the interval minus pi comma pi. As the function is even, so the Fourier coefficient in the interval minus pi to pi will be equal to 2 times 0 to pi fx dx, because the function is even. So as function is even, hence the definition of definite integral implies it as 2 times. Then an will be 1 pi minus pi to pi fx cos nx dx. Now you can see that my fx is even, cos theta is even because cos of minus theta is same as cos theta. So their product will be even. Hence it is equal to 2 times 2 pi 0 to pi fx cos nx dx. So if your function is even, then your an will be 2 pi 0 to pi fx cos nx dx. Now bn. Here we are assuming that function is even. So bn will be 1 pi 0 to pi minus pi to pi fx sin nx dx. Now here you can see that fx is even, sin nx is odd, so their product will be odd, because here if you replace x by minus x, then you will get plus fx because function is even, and sin minus theta is minus sin theta. So in the product we will have the minus sign, so we can say that fx into sin nx is the odd function. Now this is odd, so it will be your 0, because minus pi to pi bracket some odd function dx is equal to 0. Now if the function is even, then it will be your 2 times. So this is your half range cosine series, and therefore the Fourier series will be a0 by 2 as bn is 0. So this will be your an cos nx, and n is from 1 to infinity. So this is your half range Fourier cosine series. Now let us define the half range sine series. Half range sine series. Assuming that function fx is odd, then our a naught will be 1 pi minus pi to pi fx dx. Now as the function is odd, so the property of the definite integral will give you 0, and an will be your 1 pi minus pi to pi fx cos nx dx. Now again here you can see that the function is odd. Now as the function is odd and cos nx is even, so their product will be odd, and hence this value will be 0. So if the function is odd, then our a naught and an both are equal to 0. Therefore, now and bn equal to 1 pi minus pi to pi fx sin nx dx. Here you can see that fx is odd, sin nx is odd, hence their product will be even. From here you will get minus sign, again from here you will have a minus sign, so their product is plus. That means the function is even. So this will be your 2 pi 0 to pi fx sin nx dx. Therefore Fourier series in this case will be equal to, therefore Fourier series Fourier even sine series is fx equal to summation n equal to 1 to infinity bn sine nx. So this is your half range sine series. So it means in this case we will have to evaluate bn, and a0 and an will be 0, and in case of half range cosine series we will have to evaluate a0 and an, and bn will be 0. So let us solve a question related to these half range series. I am starting with question: find Fourier series of fx equal to x square in the interval minus pi comma pi, and deduce the following values: summation 1 upon n square, summation minus 1 upon n plus 1, 1 upon n square, and then summation 1 upon 2n plus 1 whole square, 2n minus 1 whole square, where n is from 1 to infinity. Again here n is from 1 to infinity, and here n is from 1 to infinity. So with the help of the Fourier series we can have the sum of these three different series. So this is the important application of the Fourier series. Solution: fx equal to x square, as f of minus x is equal to minus x whole square is equal to x square equal to fx. So it means our function is even. So this implies that fx is even. Now if fx is even, then your bn will be 0, because now we will apply the half range cosine series as the function is even. So in case of half range cosine series our bn will be 0, and a0 is will be 2 upon pi 0 to pi fx dx. Now as the value of the function is equal to x square, so the integration of x square will be x cube upon 3. So this will be your 2 pi cube upon 3 into pi. So this a0 will be 2 pi square upon 3. Now let us compute an. Bn is 0. Now an will be 2 upon pi 0 to pi x square cos nx dx. Now we can use the Bernoulli rule of integration, which is your x square. Integration of cos nx will be sin nx upon n, then we will have minus, then the derivative of x square, that is 2x, then the integration of this bracket, integration of sin will be minus cos nx upon n, so this will be your n square. We will have plus n, then the derivative of 2x, that is 2, then the integration of cos nx, which is your sin nx upon n, that means this is your n cube, and the limits from 0 to pi. Now the upper and lower limit of this term will be 0, because sin n pi and sin 0 is 0. Again here the sin n pi is 0 and sin 0 is 0, so the upper limit and lower limit of the first and third term will be 0. Here we will have the upper limit while our lower limit will be 0. So its upper limit will be minus 2 pi into, now this minus minus will be plus, into minus 1 upon n square. So your answer will be 4 times minus 1 upon n upon n square. So this is your an, and our a0 is this one. So Fourier series is, therefore Fourier series is fx equal to a0 by 2 plus summation an cos nx. So a0 was 2 pi square by 3. So this will be your pi square by 3, and an is, you can take 4 outside the summation, then in the bracket we will have minus 1 upon n square cos nx, and in the left hand side we will have x square. So this is your answer. Now for deduction, let us put different values of x in the interval minus pi comma pi. let us start with x equal to pi. Now, as the function is continuous, so at x equal to pi, the value of the function will be pi square, and here we will have pi square by 3, 4, n equal to 1 to infinity, minus 1 to power n upon n square. Then here we will have cos n pi, and cos n pi is minus 1 to power n. So the power will be 2, so the function is, the value of this minus 1 power n into minus 1 power n will be 1. Now in the left hand side we will have pi square minus pi square by 3 equal to 4. Then we will have summation 1 upon n square. Now in the left hand side we have pi square by 12. 3 minus 1, that means it will be your 3 minus 1, that will be 2, and this will be your 2 pi square by 3 into 4 1 upon n square. So your summation 1 upon n square will be pi square by 6. Therefore summation 1 upon n square will be pi square by 6. So this is your first answer. Now let us put x equal to 0. Now if x is equal to 0, then in the left hand side we will have 0, and here cos 0 is 1, so we will have 1. So if x equal to 0, then in the left hand side we will have 0, so this is equal to 0, and the first term was pi square by 3, then we have 4. Now as x was 0, then in the bracket we will have minus 1 to power n upon n. So this is equal to, let us take this term on the left hand side, so this will be minus 4, n equal to 1 to infinity, minus 1 to power n upon n square is equal to pi square by 3. Now we can combine these minus sign, so n equal to 1 to infinity, minus 1 to power n plus 1 upon n square is equal to pi square by 12. So this is the answer for the second part. So this is equation number B, and that is equation number A. Thus by A we have 1 upon 1 square, 1 upon 2 square, 1 upon 3 square, 1 upon 4 square is equal to pi square by 6. From B we have, by B we have 1 upon 1 square, then if n is 2, minus 1 upon 2 square, plus 1 upon 3 square, minus 1 upon 4 square, and dot dot, this is equal to pi square by 12. Now let us add these two terms. On adding these two equations, on addition, we will have 2 times 1 upon 1 square, then 2 times 1 upon 3 square, then 2 times 1 upon 5 square, and this is equal to pi square by 12. So, in the right hand side we will have pi square by 6 minus pi square by plus pi square by 12. So 1 upon 1 square plus 1 upon 3 square plus 1 upon 5 square plus dot dot is equal to, now this will be your 6 to the 12, and from the left hand side this will be your 24. Now 6 to the 12 plus 3, so 3 pi square by 8, 24, so this is your pi square by 8. So the summation of 1, so the summation of 1 upon 2n minus 1 whole square, where n is 1 from 1 to infinity, is equal to pi square by 8. So this is the solution of the question. Now let us solve another question. Find Fourier series of fx equal to, the question is, find the Fourier series of fx equal to minus 1 plus x if your x is from minus pi to 0, and it is 1 plus x if your x is from 0 to pi, and reduce 1 upon 1 minus 1 upon 3 plus 1 upon 5 minus 1 upon 7 and so on. and hence find the value of this summation. Solution. Now you can see that here the function fx is odd function. Why? We can also write fx as, let us take minus sign from here. So let us write f of minus x. So if we replace x by minus x, then this will be a 1 minus x, and here we will have minus pi minus x less than 0, and here we will have 1 minus x, and this is when 0 is greater than minus x, 0 is less than minus x and less than pi. And if you take minus common, now multiply. Now let us take minus sign common. So if you take minus sign common, this will be a plus pi, and now the less than symbol will be replaced by greater than. Now this minus plus, and this sign will be greater than, and 0 or minus 0 is same. Again, if we take minus sign common from here, we will have 0. Now this less than symbol will become greater than, minus plus, and again the less than symbol will become greater than, and we will have minus pi. So if you take minus sign common, and let us write this term. Now if you take minus sign common, then we can see that from here we want to take minus sign common. If we take minus common, then we will have x minus 1. So this will be your minus, let us write this term first. So this will be your x minus 1 when your x is greater than 0 but less than, when your x is greater than minus pi and less than 0. See this term. We have written this term first. So this is your x minus 1 when your x is greater than minus pi but less than 0. Then this term is 1 plus x when your x is greater than 0, but less than pi. Now you can see that this was your fx. This was the original function. So we can replace this bracket, this function, by f of x. So you can see that because f of minus x is same as fx, this means fx is odd function. So hence fx is odd function. Now as fx is odd, so we will evaluate half range sine series. So for the half range sine series, our a0 and an will be 0. So let us compute bn. Now bn will be 2 pi 0 to pi fx sine nx dx. Now between the interval 0 to pi, the value of the function is equal to 1 plus x. When your x lies between 0 to pi, the value of fx is 1 plus x. So this will be equal to 2 pi integral 0 to pi 1 plus x sine nx dx, and hence this is equal to 2 pi. Let us integrate this term, 1 plus x, integration of sine will be minus cos nx upon n, then we will have minus sign, then the differentiation of 1 plus x will be 1, and the integration of minus cos nx n will be minus sine nx upon n square, and then the limits from 0 to pi. Now this term will be 0 for the upper limit and lower limit. Now here, if x is pi, then the upper limit will be 1 plus pi into minus cos n pi, which is your minus 1 into minus 1 to power n upon n. Now for the lower limit, now let us take this minus sign common. So this will be your minus 2 upon pi. Now if x is pi, then this will be 1 plus pi into cos n pi. Cos n pi is minus 1 to power n. Now for the lower limit, we have x equal to 0. So if x is 0, then this will be your cos 0. Cos 0 is 1. So this will be minus 1 upon n. Now we can also take n common. So this will be minus 2 upon pi n. Now in the bracket, we will have 1 plus pi minus 1 to power n minus 1. So this is the bn. Okay. Now our Fourier series is fx equal to summation n equal to 1 to infinity bn sine nx. Therefore fx is equal to n equal to 1 to infinity. Our bn is, we can take minus 2 upon pi common, then in the bracket we will have n equal to 1 to infinity 1 plus pi minus 1 to the power n minus 1 divided by n sine nx. Now we have to deduce the sum of the series 1 minus 1 by 3 plus 1 by 5 and so on. So for that we will put some particular value of x. Now we cannot put x equal to 0, otherwise this term will become 0. We can not put x equal to pi or minus pi, again in that case sine and pi will be 0. So in the interval minus pi to pi, let us put x equal to pi by 2. Now if x equal to pi by 2, please remember our fx was minus 1 plus x when your x was from minus pi to 0, and this was your 1 plus x when your x was from 0 to pi. Now as x equal to pi by 2, and you can see that here your pi by 2 lies in this interval, because we are putting x equal to pi by 2, so pi by 2 will lie in this interval. So the value of the function in this case will be 1 plus x. So that means 1 plus x, and x is equal to pi by 2, so the left hand side will be 1 plus pi by 2. Now in the right hand side we will have n equal to 1 to infinity 1 plus pi minus 1 to the power n minus 1 upon n sine n pi by 2. Now let us open the summation. Now if n is 1, then you can see that at here we will have minus 1. So this will be a minus 1 minus pi minus 1. That means minus 1 minus pi minus 1. So this will be minus pi minus 2. So if n is equal to 1, then in the numerator we will have minus pi minus 2. If n is 2, then we will have sine pi, and sine pi is 0. So this term will be 0. So we can see that all the even terms will be 0, and for the odd term, that means when n is 1, 3, 5, 7, in the numerator we will get minus pi minus 2. So let us take this minus pi minus 2 common. So in the numerator we will have minus pi minus 2. Then if n is 1, this will be your sine pi by 2 by 1. That means 1 by 1. If n is 2, then this is 0. If n is 3, in the numerator we will have this term, and in the denominator this will be your sine 3 pi by 2. And sine 3 pi by 2 means sine 270 degree, and that will be your minus. So this will be your minus 1 by 3. Then if n is 5, we will have 1 by 5 and so on. Now here you can see that this pi plus 2 and this pi plus 2 will be cancelled. So now this minus and minus will be plus. Now this pi will go here, and 2 into 2 will be 4. So your answer means the sum of this series will be pi by 4. So the sum of the series 1 by 1 minus 1 by 3 plus 1 by 5 and so on, the sum of this series is pi by 4. Now let us solve one more question. Find Fourier series of fx equal to x sine x. Find the Fourier series of, let us find the Fourier series of x cos x in the interval minus pi comma pi. We can also evaluate the Fourier series for x sine x. Now here you can see that your x is odd, cos x is even, so their product will be odd. So in case fx equal to x cos x, our function is odd. So we will find the half range sine series. Now as f of minus x is equal to minus x cos of minus x, and this will be a minus x cos x, because cos minus theta is plus cos theta. So we have minus fx. Therefore fx is odd. Now as fx is odd, so your a naught and an will be 0. Therefore your bn will be 2 upon pi 0 to pi fx sine nx dx. So this will be your bn. Now this is equal to 2 upon pi integral 0 to pi, and now fx is x cos x into sine nx dx. Now let us find out its integration. We can also write it as 2 upon pi 0 to pi x sine nx into cos x into dx divided by 2. So this 2 will, okay, just take this 2 inside. So now sine 2 sine theta cos theta will be 2 sine a cos b will be sine a plus b plus sine a plus b plus sine a minus b, that means n minus 1 x dx. So this is equal to 1 upon pi integral 0 to pi x sine n plus 1 x dx. So this is your first integral. Then we have 0 to pi x sine n minus 1 x dx. Now the integration of x into sine x will be equal to x. Now the integration of sine will be minus cos n plus 1 upon n plus 1, and then we will have minus n, and the integration of cos will be sine. So this will be your sine n plus 1 upon x, n plus 1 x upon n plus 1, and then limits from 0 to pi. Let us have the curly braces. So here we will have x, and the integration of sine will be minus cos n minus 1 upon n minus 1. Then we will have minus n, therefore insertion of x is 1. So here we will have minus sine n minus 1 upon n minus 1, and here is x, and with the limits from 0 to pi. Now please note that n cannot be equal to 1, so n has to be greater than 1, because if n is 1, then we will have infinite. So here n must be greater than 1. Now in this case, the upper limit will be your sine n plus 1 into pi, as n is integer, so this will be your multiple of pi, so hence 0. So again lower limit will be 0. So first, second term and fourth term will be 0. Now for this, our upper limit will exist and lower limit will be 0, because x is 0, and same holds for this term. So now let us calculate their upper term. Now in this case, our upper term will be pi into, now we can take this minus sign common, so here we will have minus sign, and here we will have pi into cos n plus 1 pi. So cos n pi was minus 1 to power n, so this will be minus 1 to power n plus 1, and here we will have n plus 1. This term is 0, and for this term we have already taken minus sign common, so we will have plus pi minus 1 to power n minus 1 upon n minus 1, and n cannot be equal to 1. So if you take n, okay, now this minus power n plus 1 is same as minus pi into minus 1 power n divided by n plus 1, and as we know that minus 1 to power, okay, now here minus 1 to power minus 1 is same as minus 1, so this will be minus pi into minus 1 power n divided by n minus 1. Now we can take minus pi common, so in our side we will have 1, and again we can take minus 1 power n common, so in the bracket we will have 1 upon n plus 1 plus 1 upon n minus 1. So in the numerator we will have 2n, so this is equal to minus 1 to power 2n, minus 1 to power n into 2n divided by n square minus 1. So this is our bn, and it is correct. So Now as n was not equal to 1, so let us find out any b1. Now b1 will be 2 pi 0 to pi. Our b1 will be sine n is 1, so this will be sine x. As our fx was x cos x, so this will be cos x sin x dx. Now we can take this 2 common in the bracket. So here we will have 2 sin theta cos theta, that is your sin 2 theta. So the integration of this term will be equal to 1 upon pi integration x. Integration of sin x will be minus cos 2x upon 2. Then we will have minus sin. And the differentiation of x will be 1. And the integration of cos 2x will be sin 2x upon 4. And the limits from 0 to pi. Again this term will be 0. And for here the upper limit will be 1 upon pi minus cos 2 pi. Cos 2 pi is 1. So this will be your minus half. So our b1 is minus half. Hence Fourier series is fx equal to n equal to 1 to infinity bn sin nx. As we have a different value for b1, so we will write it as b1 sin x plus n equal to infinity bn sin nx. Now b1 is minus half, so this will be minus half sin x, and in the left hand side we have x cos x. So x cos x is equal to n equal to infinity. This will be a minus 1 to power n into 2n upon n square minus 1 sin nx. So this is the Fourier half Fourier series for x into cos x.